Welcome back. This is week 3 of this course on inverse methods in heat transfer. This video is about the so-called normal equations for linear models. These normal equations are methods, basically the matrix formulation for linear regression. This matrix formulation for linear regression, as you can see, is a compact form. Now, one thing, of course, is this makes things a little bit easier to code in the general case. Remember that in the last videos, we had looked at a linear model. We had also looked at quadratic models. So what we will see is that we can generalize this and make the form of linear regression work for any polynomial and also multiple variables. I had briefly alluded to this in the last week, but what we will do in this video is write one single form that encompasses all for all linear models. In the future videos for this week, we will also see that the same form can be used for things that kind of look nonlinear, but at least can be linearized. So let's proceed with this matrix formulation. So recall what we had. I'll write this as a table. Recall what we had as the general linear model. So what we used to do for a general linear model is just have a lot of data points, and we would have x, which is the input variable. In the case of the slab problem, this was the physical location, for example. And we also had y, which is from the experiment, or what I called ground truth. Apart from this, we also have y hat, which is the prediction from our model. Okay. So typically the input to the inverse problem are this x column and the y column, and y hat is what comes after we guess for the parameters of the model w. Okay. So we have a whole bunch of data points, let's say 1, 2, so on and so forth. And I had said we could have something like m is the number of data points that we have, or let's say in the case of our slab, that's the number of sensors or the thermocouples that we have. So let's say x, I'm going to write a superscript for a particular reason. x1 is the first location, x2 is the second location, so on and so forth, till xm being the mth location. Now, corresponding to this, we have ground truth or the experimental values y1, y2, so on and so forth until ym. Now, for a linear model, for example, let's say we had the simple linear model, which is our usual model, which is y hat equal to w0 plus w1x. So this is the usual linear model. This case is how we predict each one of these data points. So for example, y hat 1 would be w0 plus w1x1, and y hat 2 would be w0 plus w1x2, and in general y hat j equal to w0 plus w1xj. Now you might be wondering why I am spending so much time on this. This is because frequently as we go ahead, these superscripts and subscripts can get quickly confusing. So I just want to make sure that everything is really clear to you as we proceed. So once we use this, so suppose we guess, or for any given value of W, we have a corresponding value of xj and a corresponding value of y hat j. Okay. No, sorry. For any given value of W, given xj, you can find out y hat j. That's what I meant to say. Okay. So you can similarly find out, once you know x1, you can find out y hat 1, y hat 2, y hat m. Okay. Then you compare these two and find out the error, etc., which we did in the last week. All right. Now, what I want to do is to write this entire thing as a matrix, okay, which is one way of thinking about it is, given x vector, which is all these data points, x1, x2, I am writing this as a column matrix, xm, where each row refers to a new data point, and given y vector, which is y1, y2, ym, and also given w. Now w, for example, in our case for a linear model is w0, w1. If it is a linear model, if it is a quadratic model, then w is, as you might remember, it has three coefficients, w0, w1, w2. So our key question is this: can we write these relations, that is the relationship between x, y, y hat, and w, using matrices? Now, why do we need matrices? As you will see within this video, once you have matrices, you can generalize every single linear form of model that we will be covering, both in that we had covered in the last week, as well as we will be covering in this week. Okay. So let's come back here and look at this model. Okay. So the model here, or sorry, the data here, can now be abstracted into a simple model. Okay. So the way we are going to do it, I have done the same thing for a quadratic model here. This is for a linear model, and this is for a quadratic model. Now notice the differences between the two, and this will give you a clue on how to sort of do the matrix operation in general. Now this, of course, you can think of a serial number here, 1, 2, etc. on the left hand side. But the important thing here is that I have one column for the x and another column for the x square. Now, why do we do this? That's because y hat is now w0 plus w1x plus w2x square. And now you can imagine an Excel sheet where this whole thing is written. And what you would do in that Excel sheet, of course, is have one column for just the serial number, one column for all the x values, and then another column for x square values. And then maybe you can have a column for y hat and calculate this as some w0 plus w1, the first column, plus w2, the second column. If you had a cubic model, you would again do the same thing, except you would have one extra column for the x cube. Once again, this becomes obvious as I will go further and further within this video on how this helps us generalize to any sort of linear model. So let's look at both these cases, the linear case and the quadratic case, and now start thinking about how to abstract this into a matrix form. Okay. So the way I am going to do it is to define something called a design matrix. A design matrix is a matrix where all rows correspond to input data and columns correspond to features. Okay. For now, let's forget about this second part, which is corresponding to features, and just concentrate on input data. So if I look at this data set, the input data is purely just X. There is nothing else there. But I'm going to make a small change here. So for the linear case, I'm going to define my design matrix as this capital X, which consists of course, X1, X2, Xm. And I'm going to augment it by just 1, a constant 1 everywhere here. You will shortly see why we add this. So this really is, here is the actual data. And this we call the bias. Okay. Or let's just call it the constant term. Now, why do we do this? This will become a little bit clearer when I actually do the quadratic data. So for quadratic, my X, the design variable, for this, it's useful for you to refer to this. Now look at what the data we gave was. The data, input data was X as well as X squared. Okay. Now you might say X square can be inferred from X, but that's not the point. As far as the model is concerned, X has to be given separately and X square has to be given separately because it's multiplying different coefficients. Okay, so let's come back here. And with an analogy to the linear case, this would be 1, all these biases. Then I'm going to call this X subscript 1 because we have to put a square. Up till Xm and Xm square. So once again, this here is the data. And this here is the constant. Okay, so far we have done nothing. I have just written a new matrix X. We can also write the size of this matrix X. You can see that there are 1, 2, 3, 4 up till m rows. And in this case, you can see 2 columns. In this case, X has m rows and it has 3 columns. All right. Now let's look at the matrix W. W in the linear case is W0, W1. And in the quadratic case, W is W0, W1, W2. Now W here is a 2 cross 1 matrix and W here is a 3 cross 1 matrix. So I'm going to ask a simple question. You can see that at the very least, just by comparing the sizes, you can always do an operation like X times W because this is m cross 2, this is 2 cross 1. This has to be a matrix, some matrix which will have size m cross 1. Similarly, here XW will be m cross 3 and 3 cross 1. This will have some matrix here which is going to have size again m cross 1. Okay, so let's now look at what this matrix XW is. Okay. Let's go back here. let's look at XW. The very first row of XW is going to be first row into first column, okay, which is going to be 1 times W0, which is W0, plus W1 times X1. So this is W1, X1. Okay. Now, what does this remind you of? Let me just do it once more. Let's look at the second row, W0 plus W1, X2. And the last one is W0 plus W1, XM. Okay. Now, if you look at this, this is exactly what you would expect if you were writing the elements of Y hat. Why? Because Y hat of J is simply W0 plus W1 XJ. So this is nothing but the prediction that you will get if you put X1 into the model. So you are just going to get your model prediction Y hat. So this is Y hat 1, the next one is Y hat 2, and the last one is Y hat M. So at least in the linear case, we can immediately see that XW equal to Y hat. Okay. Now, what about the quadratic case? We can again check XW is like this. Now, let us notice what X is. 1 multiplying by W0 is XW plus X1 times W1 plus X1 square times W2, which is exactly, once again, I'll write this down, W0 plus W1 X1 plus W2 X1 square. Similarly, the next term will be W0 plus W1 X2 plus W2 X2 square. Notice that I am moving around the subscript and superscript a little bit just because we don't want to get confused with the squares. Okay. And the last term will be W0 plus W1 XM plus W2 XM square. Okay. So put together, these are, of course, exactly the predictions of the quadratic model. Okay. So once again, here too, XW equal to Y hat. In general, you can see this fairly quickly. Suppose I had a cubic model and I added one extra column here and made that X cubes, and my W's went to W0, W1, W2, W3, then once again XW will be Y hat. So we can write in general for any polynomial model, we can write XW equal to Y hat. Okay. This happens to be also the general formula for any linear model, and I will show that to you shortly. Okay. Now let's compare sizes. Okay, for a polynomial of order m or order n. Okay, so which means a polynomial of order n would look like W0 plus W1x plus W2x square up until Wn x power n. W itself will be of size W0, W1 up until Wn. So this is a n plus 1 cross 1 matrix. Okay, because of the W0, you have n of these terms, then you have this added term W0. So this is an n plus 1 cross 1 matrix. Similarly, X is going to be 1x, x square till x power n. Okay, so 1xm, xm square till xm power n. So if you look at this, X is a matrix of m rows and n plus 1 columns, and y hat comma y are both m cross 1 matrices. All right, so this is what happens when you have general polynomial models. But for general linear models, we may have more input features. So for example, we could have a case where we have, instead of one dimension, two-dimensional models. So for example, we had temperature as a function of x in one dimension, but it could be temperature of x comma y. And since we don't want to confuse the y, which is also an output variable, we are going to call it x1 and x2. So instead of a slab, let's say you have a plate and you want thermocouples at a lot of places, you need a model which depends on both x as well as y location. And of course, three-dimensional, let's say you have some semiconductor, stuff like that, and you have a chip and you want a temperature model within there. Of course, now it is going to be a function of three variables. So 3D, you will have things like t of x1, x2, x3. Now, let us say you have a case like this, and you have a linear model. Now, these things here are called features or attributes. Okay. It's more accurate to call them attributes, but I'm going to call them features. We, of course, call them, in the usual language, independent variables. Now, let's say you're solving an inverse problem with not one independent variable, which is the only case that we did till now, but we are looking at multiple independent variables. What does that look like? Okay, so in this case, if you have multiple features or multiple independent variables, let's say you have a temperature model, then you could have the temperature, which I'm going to call y hat again as a hypothesis, would depend on W0 plus W1 x1 plus W2 x2. This would be the linear model in two dimensions. Okay. Notice here I have used a subscript to mean the dimension, okay, and not the data point. Ideally speaking, if you have multiple such sensors, let's say you have 7 such sensors here or 8 such sensors here, then what you would do is, suppose I want the 4th sensor, let's say, or the 5th sensor, then I would say something like y hat of 5 would be the x location of that 5 multiplied by W1 plus the y location of 5 multiplied by W2 and plus some extra term. Okay, so this would be a linear model. Now, what happens to a quadratic model? So that would be something like, so suppose we know that the temperature also has a heat source such that the entire thing is going to be quadratic. Then you would have something like y hat equal to W0 plus W1 x1 plus W2 x2 plus W3 x1 square plus W4 x2 square plus a quadratic model would also have cross terms, let's say W5 x1 x2. Now this looks like a very, very complicated model, but luckily this is where our matrix formulation is extremely helpful. So I want to point out again, this is a general model that handles linear, quadratic, any type of polynomial, and it also handles multiple dimensions or multiple features. Now, how does it handle that? By a very simple trick. Let us take this expression. Okay. I'm now going to call it y hat equal to w0 plus w1 x1 plus w2 x2 plus w3. I'm going to call it x3. Okay. Plus w4 x4 plus w5 x5, where it is our understanding that x3 corresponds to x1 square, x4 corresponds to x2 square, and x5 corresponds to x1, x2. Now you might say that, but this is not linear. The point is, it need not be linear in x. Why? Because these are given data points. The problem we are solving for is the problem of solving for w. So all that matters is for linear models are linear in parameters. And not in features or independent variables. For example, when we had a simple quadratic model such as this, it was not linear in x, but it was linear in w. Okay, so it is only w0, w1, and w2. You don't have terms like w0 square, w1 square, w2 square, etc. All you have are terms that are linear in w. When you look at this formula, x w equal to y hat, the main thing here is this is linear in w. X is basically a constant matrix, so it doesn't matter whether it is linear, non-linear, whatever. So for example, I could make up a model with an additional term if I wish, like w6 times x6, where x6 could be sine of x1. Okay. Anything of that sort is still linear as long as you have only w6 here and not w6 square or w1, w2, w3, w6, etc. As long as that is the case, this model is always linear. Now, the second thing is, when we look at an Excel sheet or that kind of format, all you need to do is you need to substitute. You had x square here and y here in serial number. Instead of that, you will write x1, which is the x dimension. Then you will write x2, which is the y dimension. Then you will write x1 square as another column, x2 square as another column, so on and so forth. And you can actually make up an entire design matrix that way. For example, in this case, the design matrix, capital X, is going to look like a whole bunch of ones. And then after that, x1, x2, and we will go up till x5. Remember, these are just columns of our Excel sheet, except for this first column. This first column is just added, tacked on, just to make the matrix multiplication work well. Okay. So after that, this will be x1 at the first point. This will be x2 at the first point. Remember, each one of these corresponds to the thermocouples. The superscript corresponds to the location of the thermocouple, and the subscript here corresponds to our Excel sheet entry. The first two are simply the x location and the y location. The third one would be, as we already know, x3 was x1 square. It is the square of the location. x4 is the square of the y location, and x5 is x location into y location. Okay. And then w is w0, w1 through w5. And once again, if you see the model, it looks exactly the same. Y hat equal to x times w. Okay. Y, for example, at the first point, y hat would be w0 plus w1 x1 plus w2 x2 up until w5 x5. Okay, so you can basically use this matrix in order to write the relationship. Now for any linear model, not only the linear model that we saw, which was very simple W0 plus W1x, but this is true in general. So this is the general expression as I wrote. Okay. For any linear case. Okay. But how does this help us solve the optimization problem? So let's look at that now. Okay, so solving a general regression problem. Now, if you recall, last week, we had two independent solutions. Okay, even though there was some pattern that we could notice, there were two independent solutions for a linear case and for a quadratic case. And you can imagine rederiving it for a cubic case or for a case where you are in 2 dimensions and you have multiple, you have 2 dimensions and quadratic or 3 dimensions and cubic, etc. That becomes more and more messy. Can we write one single expression that works for every case? And we are going to do that. This is what is called the normal equations. Approach. Okay. So our model is as follows. I am going to use a couple of notations. Notations are this. If I say some vector v, this thing is called norm of v squared. This is how we pronounce it. This part is called the norm, okay, with the double absolute sign. That part is called norm of v. This is nothing but all the components of v squared summed. Okay. So if v is a vector which goes from v1 to vn, norm of v square is v1 square plus v2 square up till vn square. Okay. Now another way of writing this is v transpose. If v is this matrix, v transpose, all of you would be aware, is basically just the transposed case. Okay, it's the row matrix and v is the column matrix. So v transpose v, you can now see, is v1 square plus v2 square up till vn square under the usual, is the same as norm of v square. Okay. Technically speaking, you are supposed to call this the 2 norm of this, and I'm supposed to put a subscript 2, etc. All that I'm going to skip, at least for now. So this is v transpose v. Okay. Now let us come to our loss function. So the objective function or the loss function that we are minimizing, j, was half of sigma y minus y hat whole square from I equal to 1 to the number of data points. Okay. Let's call this EI, okay, where EI is the error in the ith data point. Now, of course, E itself is a vector. E itself is a vector. E1, E2, up until EM. Okay, so it's an M cross 1 vector. So this E is now a M cross 1 matrix. Now what we want to do, of course, is express J also as a matrix. So remember, we had expressed X, W, Y hat all as matrices. So J also we want to represent in a matrix form. Remember, J of course is a scalar. So this is half of, now you can see, norm of E square. Why? E is a vector and E vector is basically Y vector minus Y hat vector, and E square, each element of E squared and added just like before, this V example is what is happening here. So this is norm of E square, and which we just saw, norm of E square is nothing but half of E transpose E. Okay. So another way of writing J is to say J is half of E transpose E. Now, opening up E, this is half of Y minus Y hat transpose Y minus Y hat. And we can open this up further. This is half of, let's take each term, Y transpose Y. So Y transpose Y minus the second term Y hat transpose Y minus Y hat transpose Y. The third term Y transpose Y hat. So minus Y transpose Y hat. And the final term, which is plus of Y hat transpose Y, plus Y hat transpose Y hat. Okay. So these are the four terms. This is, of course, equal to J. How is this useful? I am going to take one further step. Remember that we have a model for Y hat. Sorry, Y hat. We had the model. This, of course, is an entire vector. X times W is equal to Y hat. Okay. So Y hat is equal to X times W. We can also write Y hat transpose, which occurs in a couple of terms. Y hat transpose is X W transpose, which is W transpose X transpose. Okay. So we are going to substitute these expressions here and write them out now. So J equal to half of, I'm going to use capitals here to indicate that they are vectors. Vector signs would get a little bit messy. Minus Y hat transpose, which is minus W transpose X transpose Y, that is this term here. Then the next term, minus Y transpose times Y hat is just XW. Sorry about that, XW. And the final term is Y hat transpose Y hat, which becomes plus Y hat transpose is W transpose X transpose, Y hat is XW. So remember, this is Y hat, this is Y. So this is what we wish to minimize. So what we wish to minimize, the minimization problem is minimize J with respect to all possible values of W. Okay. Now remember, J is a scalar, so it is only one function which we are minimizing, but W is a vector. It's a vector of values which goes from W0, W1 up until Wn. Okay, so N we will treat as, in general, the number of features, and M in general as the number of data points. This is the notation that we'll be following. Now, this is the giant function. It doesn't look like we have simplified. It looks like we have complicated things. But as you will see, this actually simplifies things. Now, although in the beginning of this video, I started out saying that we will do normal equations, this video is already a little bit long. This is the objective function we want to minimize. And in the next video, I'll start with this objective function and minimize this with respect to W. So see you in the next video. Thank you.